Good morning, everyone. For the last few months, I've been working on how we can enforce determinism in LLMs through using fixed point reductions. So at the moment, there's a problem in LLM inference where when we're decoding, even with a temperature of 0, we can get different output sequences just dependent on the execution context. So a paper published in 2025 found that over the AIME benchmark, 100% of the tasks had different outputs when changing the environment. And this translates to a 9 percentage point change in output accuracy. And for the reasoning models they used, this is a 9,000 token shift in output length, which is a sizable change of compute. And so downstream, this means that evaluation is a function of the environment. It means that safety auditing isn't as reliable if we can't trust the environment that the LLM is being run inside. And on top of this, if we're doing on-policy reinforcement learning, which relies on the equality between outputs of training and inference, if these environments change, it undermines the efficiency of the training. So in this work, we hope to contribute 3 things. The first of which is a characterization of where this noise comes from. The second is a set of fixed point kernels built in Triton, integrated into the LLM, and then benchmarked against current batch invariant solutions to see the downstream performance trade-offs in throughput and accuracy. Before I get into the content, there's a few things I want to go over. The first is the prefill decode split. So when we're doing LLM inference and generating tokens, this is split into 2 phases. The first is prefill, where we're computing the input tokens. And this is a compute-bound operation. The second is decode, which is a memory-bound operation. It's when we're generating tokens one at a time. The second is the idea of an LLM serving engine. So this is the engine in which an LLM is run. They're built to make efficient use of resources to maximize throughput. And for the sake of this work, we're using LLM, which provides its own batch invariant mode, which we benchmark our solution against. And then finally, the idea of an execution context, which is just a set of all variables which are present within the environment. So things from architecture to resource utilization and other programs running at the same time. So there's many variables which can influence variance, and this work focuses specifically on batch size and how that influences variance. We also look at how GPU architecture influences this batch-induced variance. And while GPU count is important for splitting tensors between multiple devices, this is left as future work and commented on at the end. So where does this variance come from? It's a combination of 2 factors. The first of which is floating point non-associativity. So if we can't represent a number in a floating point representation, we round it. But this creates a scenario where, dependent on the order of operation, we have different rounding errors introduced, which then cascade into different outputs. As I mentioned before, LLM serving engines dynamically change the batch sizes to fully saturate GPUs and maximize throughput. What we have, though, is a scenario where, dependent on the order of operation, dependent on the way that a certain input is batched, we get different outputs due to the different rounding errors that get incurred. Now, so what are we trying to enforce? We're trying to enforce this idea of batch invariance that says, given a single input prompt X, 2 batch sizes, a seed, a set of hardware, and a system, we want the output of this system for this same prompt to be identical under any batch size. So the way that current solutions do this is to fix the order of operation. And while this works, it incurs a throughput cost as a result of 2 scenarios. One where you have cores that are underutilized because you can't further split up the work at the risk of breaking the order of operation. And 2, where you have to use a suboptimal scheduling scheme to maintain this order of operation. So what we propose is to say the inverse. And instead of fixing the reduction scheme and foregoing some optimizations, we introduce associative arithmetic through fixed point operations so that we can recoup any optimizations that we would have lost through the other approach. And the rationale of using fixed point numbers is threefold. So first of all, addition is identical in terms of bitwise manipulations. So we can use a lot of the GPU infrastructure built for integers, but for our fixed point numbers. The second is that LLM decoding is memory bound, and casting to and from fixed points would be a compute cost, so we won't have to incur as much of a performance hit as we would. And finally, fixed point addition is associative. So it means we can still use optimizations like split K and matrix multiplications or atomics, for example. So this first section is to characterize where the variance comes from. What you can see here is 2 models. each grid cell's color represents the fraction of prompts over the AIME dataset that are identical between two setups. And the setups can be derived by looking horizontally to look at a certain batch size and GPU configuration, and then vertically as well. And we can see a clear diagonal where the setups are identical and all the prompts are identical run to run. But aside from this, all the prompts are near zero, they're near zero identical prompts. We can look closer by investigating the input and output tensors from each module and see that there are three surfaces that give rise to this variance. And then further down, we can see that the operations that call these modules, the variance surface is sometimes, in the case of LM head, dependent on the GPU. We can look at the KL divergence between the probabilities in different batch counts and see that the variance onsets pretty much as soon as the input prompt ends. And the magnitude of this variance is capped at about 2, but can go all the way down to 2 to the minus 13. So the key takeaways from this is that there's three surfaces that we need to implement. The variance incurred is dependent on the GPU, and the use of fixed point numbers as accumulators is sufficient given the magnitude of the variance. In this section, we outline the implementation. We first build Triton kernels, we patch them into PyTorch so that CUDA graphs can be registered. We build a plugin for VLLM, and then design a warm-up scheme for this plugin. So the core idea that these CUDA kernels are built around is that if we have a list of floating point values and we want to reduce it, we'll first cast it to a fixed point, onto a list of fixed point numbers, reduce it, and then cast it back to floating point. But it's rarely as simple as this outline, and matrix multiplication is a good example where we need to use tensor cores because they offer a 40 times the throughput of normal CUDA cores. But the caveat is that tensor cores don't support these int16, 32, and 64-bit types that we've been using to store our floating point numbers. So what we do is we define a fixed block size, use tensor cores to operate on these, and then take the outputs, cast them to fixed point to perform the reduction. And in a similar way, we can implement split K by using atomics, accumulating the atomic in integer form after casting to fixed point. Attention is another interesting implementation where of course, within the attention equation, we have a softmax. And in the denominator of that softmax, we're summing a list of exponentials. So flash attention does this by using a running max variable. The caveat of this is that this running max is tied to the specific tile you're in and the tile size, which in turn tied to batch size, which is a source of batch variance. So what we do instead is do a two-pass system where in the first pass we calculate the row-wise global max, and then for each tile we use this global max so we don't have to accumulate this running max that is dependent on batch size. And this way we can maintain this O of n memory accesses rather than the n squared you get from typical attention. So how this looks in the system is we have our set of Triton kernels that we built. We patch these into PyTorch so they can be found using CUDA graphs and VLLM. We then expose three surfaces and integrate them into a VLLM plugin so that the user can turn on this mode just by specifying a quantization and attention backend. And so this next part is talking about the benchmarking, and there's a few integral questions that we want to answer here. The first is our system actually batch invariant? We then want to see the trade-off in terms of accuracy and performance of our system with these fixed point kernels. We want to see how this compares against the current state-of-the-art batch invariant models, as well as a non-batch invariant baseline. And then we perform some ablations to see the influence of the different components within this plugin. So what you see here is the same graph from the earlier slides, but between the three different engines. On the left, it's a VLLM instance with no batch invariance, and as you can see, there's next to no identical outputs. In the center, you see the model using fixed point reductions, FxPR, which has full batch invariance, and additionally GPU invariance between the A100 and L4 GPUs. And on the right, you see the thinking machines approach of fixing the reduction order that exhibits batch invariance between only two of the GPUs. On top of this, we can see across two different benchmarks that there's no significant accuracy degeneration across any three of the engines on either of the GPUs or either of the models. But the best outcome was in performance, where we found that, so here you see two models. The purple is a Quen model and the pink is a large llama model. The dotted line is the fixed order implementation. the solid line is a non-deterministic baseline, and the dashed line is our fixed point kernels in the VLLM system. And you can see we forego almost no throughput up until about a concurrency of 64, at which point our plateau seems to onset earlier than the other two engines. We can take a closer look at the TTFT and the time to first token and the inter-token latency and see similar patterns in the inter-token latency of next to no penalty until the end, where we start scaling more poorly. And then conversely, in the time to first token, which is essentially timing our prefill, an operation that's compute bound, we can see we pay a significant tax over the other two engines, likely because this is a compute bound operation and we're adding additional compute in the costs. Finally, we perform some aberrations to see how much influence each of the components of the patches contribute to the batch invariance. And you can see overwhelmingly that gem contributes the most invariance, and conversely is responsible for most of the performance degradation in comparison to a baseline engine with no determinism. We also vary the bit widths of these fixed point accumulators to see how the model responds regarding accuracy. And the takeaway from this is that you need about 12 bits of dynamic range and about 6 bits of precision for the models we tested. And whether the accumulators saturate or not is a case of, it's a binary case where we either completely get no accuracy or we achieve the same accuracy as we would have otherwise. So the takeaway from these results is that we achieved batch invariance with no accuracy degradation and nearly no throughput tax. And so where does this go next? There's a few things to look at, and there's definitely a lot of room to be made in terms of tuning and diagnostics. So, for example, we could set up a system to profile a model's distribution of values through the accumulators and set up the fractions and bit widths such that we can be assured they are bespoke for each implementation, each module within the model. We could also propose a hybrid approach between a fixed order, which performs better in prefill, and a fixed point reductions, which perform better in decode. We should also see how this method scales with larger model sizes, and for that, tensor parallelism is a very useful feature to have, and this is just another hierarchy up of using fixed point numbers than what we have at the moment. Extending this to other hardware as well is very interesting. So, for example, AWS's Trainiums or Google's TPUs. Another sort of tangent from this is that we could use the int8 tensor cores that exist to potentially not have to do the cast in gem and not forego this throughput penalty and maybe have determinism at a lower cost. And finally, extending this to other LLM models. So, for example, we've had proof of concepts of it working with mixture of expert and reasoning models, but there's no reason why this method can't be integrated in other ML systems. So just to conclude, what we did in the characterization is build a set of tools to diagnose batch invariance within models. We ran a sanity check to make sure these tools don't interfere with the output tensors, and then found the specific sources of variance within the models. Regarding the implementation, we created a suite of fixed point Triton kernels and benchmarked them against the cuBLAST baselines. We integrated them into VLLM and then optimized the system using a custom warm-up schedule for the JIT-compiled Triton kernels. And then finally, for evaluation, we achieved full batch invariance over the GPUs we were targeting and partial GPU invariance between the L4 and the A100 GPUs. We got no performance degradation as a result of using the kernels. We beat the current batch invariant methods on a throughput and end-to-end latency. And then we also performed an ablation to quantify the effects of each component within our plugin. So yeah, thank you to Marius and Holger, of course, for being great supervisors and assistant. And thank you.
Sure. Okay, let me go bottom up. Can you go back about 3-4 slides? Yeah, this one, no, this one.
Yeah.
Sorry, you went through this quite quickly and you drew some kind of inference. You said you need, what, 6 bits?
So 12 bits, I guess, within the head of the accumulator and 6 bits in the bottom. And the reason this was drawn is because we can see with all bit widths, until we get more than 6 bits of of fractional component. And until the fractional component is more than 6 bits, the accuracy is 0. And conversely, if we have less than 12 bits in the whole number component, we also go to 0.
I see. And how does this generalize? Or would, like, any idea?
How would this generalize?
Generalize to other models?
I wouldn't, unless, so the models we used here were Quen 3, 0.6b, and Llama 3.18b, and these just happen to have the same dimensionality. But I'd be hesitant to take extrapolation to larger models, because we don't know how that extends.
So how do we find out?
We should test on bigger GPUs that can have more weights in.
So try
more data
throwing
centers.
stuff at the wall and see what sticks. I don't know, can we like have a bit more of a structured approach? What would you...
Yeah, I think definitely looking at it on probably a kernel-specific level. So this was accuracy over the whole system. We did unit tests on the specific kernels for correctness, but so when we're doing these unit tests, we could potentially say what are the dimensions being reduced over, say, let's say in the language modeling head of each model, and then perhaps draw a relation between size of the model dimensionality and the bits required, fractional bits required for correct output.
Okay. And then could you go back to your throughput evaluation? Yeah, this one, like all of them.
Okay.
You cut all of them at concurrency of 256.
Yeah.
And then you made a claim about, like, not paying a throughput tax.
Up to...
And I'm saying, sure, for the range that you've studied.
Peak throughput is definitely less. The reason I didn't extend it higher was because we were using 3 GPUs, 2 models, and 3 engines, which is about 18 configurations in total. Up to this point on this GPU took about 2 days. So extending it by another factor of 2 times another factor of 18 was out of the scope for the time being. But definitely that's like a really important thing regarding peak throughput. And as this scales to models past 8B, I reckon that's like a integral point of concern is peak throughput.
Right, but maybe it would have been good to reduce resolution here. Maybe go in increments not of factor 2, but of factor 4 or 8, and extend this further to the right. Because right now I have no idea, like I suspect the fluxion's off somewhat.
Yeah, yeah. Across the other GPUs, I don't think I've got the graphs in here. They're in the report, in the appendix. But yeah, you do see this plateau, and it's commented on. But yeah, in timing this, I was very close. But today, I think I did a bit quicker.
Okay. And then, like, maybe my last question is, like, you made the engineering sound very, I'm going to say easy, right?
No, it was not easy.
Yeah, exactly. But the thing is, like, a lot of projects sound like this at the end. At the end, you think, well, yeah, sure. And then you just did it.
Yeah.
I suspect you didn't just.
No. So, obviously when I was making the presentation, there are some things that had to be cut and interesting.
Yeah.
But to elaborate more on the implementation, the correctness of it, so originally this was implemented in CUDA, and the correctness of the kernels themselves wasn't too bad to do. Implementing it into VLLM and building a system that was competitive was extremely difficult, specifically because we were tuning 5 kernels over these 3 GPUs, 2 models, massive space. So then we switched to Triton, which again was, translating all that code is a big chunk of work. And on top of that, we had to redo the tuning. But the interesting point here is using Triton, the kernels are JIT compiled. So we had to come up with a method which is talked quite extensively about in the report, about warming up. Because there's 2 costs that are paid when you run for the first time. There's one of the compilation, but also of the auto-tuning of each kernel. So we create a system where we pre-tune everything in the warm-up, pre-compile and cache it. And then so when we run in practice, we're not exposing that cost. Yeah, I mean, I don't want to describe how difficult implementation, but yeah.
All right, yeah, I can go next. Thanks for the presentation. I have a question about the accuracy, because you focused a lot on performance, and I would like to understand this better, the kind of experiments that you run in order to quantify accuracy, and also at the higher level, how can we be principled about this? Are there specific kind of questions that they might be more forgiving compared to other ones? So if you ask a yes/no question, for example, evaluating the accuracy might be straightforward, but then if you have a more complicated answer, how can we judge that?
Yeah, that's a really good point. So there's a few factors at play, one of which is the scale of the models, which are not very capable compared to today's standards, which means on a lot of benchmarks, especially if you have a few questions, the answers tend to degenerate, and you'll get, let's say if you're using random sampling, maybe 40% in one run and then 26% in the other. So for the sake of benchmarking, it was important to use data sets or benchmarks with 500 plus questions. So we have that range. In terms of correctness and what does it perform better on, of course, dependent on the model. I'd be hesitant to make claims again about what are some things that it does well and some things that it does worse, because I don't want to reiterate it's a black box and people don't really know, but to be determined, right? These models we used were base models rather than reasoning models. And of course, when you have reasoning models and lots more tokens, not only is it more susceptible to batch invariance, but there's more of a risk of if there's any quantization happening or loss of information in it during the process of that playing an effect. What could people do to have more confidence in the accuracy? Again, I guess kernel level tests is a big one in terms of correctness and validation against baselines. But then also, as I mentioned at the end, potentially tuning individual accumulators to minimize the risk of overflow. That could be another factor there. Yeah.
Okay, cool. And then kind of a provocative question, but great job you did for one GPU. Everyone is doing distributed inference.
Yeah.
Do we start from scratch?
No. So if I go to this slide here, of course, the scope of this project was batch invariance, and GPU invariance was a cool byproduct of that. And in looking into why the Blackwell RTX GPU was not invariant with the other two GPUs, I found that the source of variance was outside the targeted modules. So it's not so much a ground starting from zero, but it's more that we know where to look and where not to look. We know that, I would speculate, the reason that these two have GPU invariance is because they both are very similar compute capabilities. It's 8.0 and 8.9, which dictate the optimizations that are used on a hardware level for implementation. So yeah, in terms of distributed compute, if we were using the same GPU, tensor parallelism, as far as I know, that should be one more module implemented in VLLM. And then same GPU, theoretically, you should get the same output. Cross GPUs, interesting question. I think the same sort of methodology of using the tooling in the characterization, finding sources of variance, seeing specifically where the rounding errors incurred, and then building a kernel for that should suffice. But it'd be interesting to see. There's some cases like in the RTX Blackwell GPU that in testing, some kernels were changed depending on the batch size. So batch size 1, they'd use a vector multiply, for example. Batch size n, they'd use a matrix multiply. And so I'm sure there's loads of specific things like these two GPUs that are done in the interest of tuning that would need to be looked into.
Okay, cool. Last question for me, what comes next?
To be determined. I've got some offers on the table, but I'm not rushing into anything. I'd rather find something that's lucrative, like economically, but fulfilling as well, to do. And so I really enjoyed this. Definitely over summer, I'm going to be revisiting this, especially the int8 tensor cores alternative. I think that could be a really cool way to achieve determinism. But yeah, thank you.
Right, thank you very much. Best of luck.